Here we go. All right, ladies and gentlemen, welcome to Wednesday that feels like Thursday. Do you feel that way too? I'm totally feeling, I'm like, oh, we're almost there. It's great. Some logistical things to get started. No, I do not have your tests graded. I am sorry. I was here until 7:15 doing conferences. Then I had to go vote, and then I had to watch a terrible game that didn't end until after midnight, and then I just went to bed. So it is now the next day, and I have not graded them yet. Not everybody's taken it anyway. I will get them to you as soon as I can, though. Okay, it's like the top of my to-do list, so hopefully I can get those at least started tomorrow. I probably will get them back to you on Tuesday. That's my guess. Other logistical stuff. I need you to hand in your reaction time labs if you have not done so yet. So I'm going to give you just a couple seconds. If you need to turn that in, to bring it on up now. I know that I've got a bunch of them, but if you have it, if you need to turn it in, now would be a good time. So come on up and do that. Come to me, put it in the box. Thank you. Also a friendly reminder that I think that the free fall lab, if you have not yet turned that one in, by that I mean shared it with me, is also due this evening. Is that correct? Does anybody have questions about that one? So that's the one where we're dropping balls off the balcony. We made the graph. It took us a few days to figure out exactly how to graph things. We got the graph. You got the line of best fit with the slope. You wrote a conclusion. You shared it with me. If those are not past tense for you, make sure that they are by the time you go to bed tonight. Okay? Questions about that? Does that make sense to everybody? Okay, cool. All right. We are going to start a new unit today, so that's exciting. Oops. Go away. Basket. Yep, right over there. Would be great. There, freeze. All right. The Unit 2 calendar is now posted. I got it up this morning, so just a couple of things to know about it. Unit 2 is going to be much shorter than Unit 1 was. Unit 1 had a lot of getting started stuff, so this is not going to be another 6-week unit. I promise. It'll be about 2.5 weeks by the time we're done. The plan is at this point to just do 2 homework quizzes as well as some problem work. So we're not going to have a test at the end of this unit unless by the end of the unit I'm like, wow, we totally need another chance to assess so that you can feel confident about what you've done. But I don't anticipate that we'll have another big test at the end of this unit before we move on to the next one. The topics for this unit are projectile motion, which is going to be super awesome, and then also an introduction to vectors because we're going to need them this unit, and then we'll also need them next unit. If you have done vectors in your math classes, that means that they were hard in math, and now they're going to be easier now. If you've never heard the word vector before, this will be the time when you get to learn them, and you're lucky because I love vectors and I love teaching it. So I'll be all over it. We'll get it. It'll be fun. That will happen in a week or so. So something to look forward to. Let's see. Tomorrow, this is very important. Tomorrow, we have a lab. It is not in this room. You need to meet me at the stadium tomorrow. Okay? This is the best lab of the entire year. It is fantastic. Do you remember when we went out last year? No, it was great, though. I remember you thought it was great. It is great. You're going to love it. We're going to go out to the stadium. We went outside. You were there. I remember it. It was great. We're going to meet at the stadium. The thing that I want you to know for sure is, number one, do not come here. If you come up here and then try and get there, you will be late. You will miss things. We do not have a long period. It's a Thursday, right? So we need to get there as quickly as possible. If you have a 4th period open, then make sure there's no excuse, right? Do not be late. Make sure that you have shoes on that you can run around in. Okay, so if you're wearing flip-flops or even probably Birkenstocks, you want to make sure that you bring other shoes so that you can run around. And also, it's 83 or something crazy like that today. It's going to be something around 63 tomorrow. So make sure that you have a sweatshirt or whatever it is so that you're going to be comfortable, because I don't want to hear about whining. I want to do physics, not whining time. Does that make sense? Okay, it's going to be great. I love it. It's so much fun, but you need to make sure that you come to the stadium because that's where we're going to be. Got it? Sweet. All right. Also, just because I don't want to forget to tell you tomorrow, there is some homework for Tuesday, which is the next time that we will see you, we'll be in here together. And it's up on Canvas as well, but it's right there as well. Good for logistics? Your family had very, very lovely showing at conferences yesterday. So thank you to those of you who sent your parents or brought your parents or whatever that meant. That's awesome. But know that I heard some rumblings from the other classes that I've talked to so far, like, oh man, we totally got to overtake them. So don't forget, if your parents didn't come visit me last night, to remind them to come next Wednesday from 4:15 to 7, or anytime between now and then, if they call me or email me and check in, then that counts as well, okay? Questions? I have candy. It was fun, right? It's good time. So anyway, that's just the other little piece that I wanted to say. All right, you ready to go? Okay, we're going to do a couple of warm-up problems to get our brains, moving and ready. There are some cute kids. All right, let's do this. All right. Here we go. 2 warm-up questions. Warm-up question number 1. So you need a paper out, you need a pencil out, you might need a calculator out, maybe even an equation sheet. These are the things that would be good for today. Question 1. If a ball rolls 4.2 meters with a velocity of 1.1 meters per second. Actually, I really want to say is, how long does it take? That's what I really want to say. How long does it take a ball to roll 4.2 meters with a velocity of 1.1 meters per second? Question mark. There we go. Now I've got it written well. How long does it take a ball to roll 4.2 meters if it has a velocity of 1.1 meters per second? Absolutely feel free to talk to each other. This is not a test. This is a getting our brains in the mindset and the mode that we need to be in for Unit 2. Wait, I did this in Unit 1. No. Unit 2 builds on Unit 1. They all are related. How are you going to start the problem? Givens! Absolutely. Write down those givens. You got this. You have an equation for that, don't you? Did you pick an equation? What equation did you pick, Zach? V equals delta x over t. That seems like a reasonable choice, doesn't it? Yeah, because it's all there. We have to solve that for t. T equals, what's that going to be, delta x over v? Do we get an answer? No? Thomas, did you get an answer? 3.82 seconds. 3.82, is that what you said? Okay, I just want to make sure I heard you right. How'd we do? We okay? Sweet. I want to do two more little things with this problem. If you were going to draw a displacement versus time graph for that motion, what would it look like? You don't have to put points in there, just draw the sketch of it. What's it going to look like? What'd you say, Sam? I didn't say. You didn't say anything? Why don't you talk to your table mates? All of you, have a conversation. If you don't know, talk to your table mates. What's it going to look like? You can dance it out. You can just talk. You can speak in Pig Latin. All right, Sam, do you have an answer now?
Yeah.
Sweet. Like this?
Yes.
Yes. Fantastic. If you were going to use some words to say like this, Leanne, what would those words be that you would say instead of just saying like this? I mean, it was good. It was clear, but constant slope. Awesome. It has a constant slope, so it keeps moving away and away and away and away. Does that make sense? Constant slope. I'm putting all this together. There's a reason for it, friends. So I need you with me. You're like, I got this. We got this like 4 weeks ago. I understand. Yeah, it has a constant slope, which means, tell me about its velocity. Constant velocity. So now I'm going to show you one other way that one might draw a picture with this ball. So I'm going to imagine this ball is just rolling along some sort of horizontal surface. We're going to assume that there's no air resistance, no friction, because we like to live in a vacuum. I mean, not literally, because then we wouldn't be able to breathe, but we like to imagine that all physics happens in a vacuum because then we don't have to deal with all these messy things. So here is my object at a few different times, and I want to draw some arrows to indicate its velocity. Does that make sense? So I'm just going to draw arrows to indicate its velocity. So here's my first arrow. So you go ahead and draw that as well. And then with the help of your friends or with the help of your brain or whatever you need to do, draw some arrows on these ones to indicate what's happening to its velocity. A longer arrow would mean that it's going faster. A shorter arrow would mean that it's going slower. A same size arrow would mean that it's not going faster or slower. All right. Amanda, are you guys there? Did you get something? What did you say?
That the arrows are all the same.
The arrows are all the same all the way through, and why is that? Awesome. That is all review stuff, but are we okay with all this? Is there anything wild and crazy that's just happened here that you have questions about? Okay, that was question number 1. Here comes question number 2. How long does it take a frog dropped from 1.6 meters above the ground to hit the floor? Just starting another problem, right? Always starting your problems with some givens. Then you're going to use that equation sheet to find an equation. Be clever, solve the equation, come up with an answer. Those are the things that you should probably have written down as your givens, yeah? D, V, I, A, and T. There's one equation that you're getting to know really well. Okay? So well that I would strongly advocate if somebody feels moved to get some shirts made that say, I heart this equation. What's the equation, Lily? What is it?
Delta x equals initial velocity times change in time.
Uh-huh.
Half of acceleration times change in time squared.
Awesome. If you decide to make these t-shirts, please put me in for one. I would love one. I love delta x equals VIT plus 1/2 AT squared. And you will too. This, Thomas, you don't believe me, but it would look good on you. I'm thinking we do bright colors. You could do tie-dye. I don't really care, but it would be great. This is it right here, friends. This is going to be the answer to most of your, what equation am I going to use this unit? Okay. Just letting you know. Spoiler alert. That is it right there. All right. What givens did you have written down? I mean, that's the list of them, but did you have any values for any of those? Go, Zach.
The acceleration is -9.1 meters per second squared.
Indeed. And we can have that. You could take or leave that one. I don't feel strongly about it. I'm not gonna get bent out of shape. Yeah. What other givens do you know? Cara, what's another one you know?
1.6 meters.
1.6 meters is the what? Is the distance. Is there anything that we need to make note of about that distance or that displacement? It's negative. It's going down. That down matters. Why does it matter in this case? It cancels out the negative of the acceleration. Just get square root of a negative number otherwise, and that would not be good. All right, one more that we need. 0. Yes, zeros are good. The velocity initial is 0. We know that because it's dropped. All right. We like that because why? What happens to our big, long, scary equation? It gets shorter. We say, yay, short. That's good. We can be clever. VI is 0. VI 0 times anything is 0. That makes our life better, right? Then we can solve this for T. So T is equal to, you want me to go through that? What do we do next? To get TL by itself? Divide by 1/2 A. And then I've got just a T squared. Ooh. How do I undo that T squared? Square root. Get rid of that squared. That's going to cancel out with that. So you've got T is equal to the square root of delta X over 1/2 A. How are we doing? We okay? Fantastic. How long does it take? Did you guys get an answer?
0.33 seconds.
Point what?
0.33.
0.33. Do we agree? Did you square root it? I'm thinking no, because because that always happens to me. When you square root it, it's going to be 0.57. Double check that, Zach, and make sure you agree with him or agree with that because I want to make sure that it's feeling okay. Let me know. How are we doing, team? Okay. Here's my next question for you. We're going to do the same kinds of questions that we did for the other one. Can you draw for me a displacement versus time graph for the frog falling? Oh, that's interesting. Can you draw for me a displacement versus time graph? Talk to your table mates if you're not sure. That's kind of a weird one. We haven't explicitly done this before. Hey, thanks. It might be helpful to go backwards, to work backwards a little bit. What is the acceleration versus time graph going to look like for my frog that's falling? Go ahead. Go.
It's gonna like curve up.
Which one?
Acceleration.
The acceleration? Does the acceleration, so it's going to go like this? Zoop.
Yeah.
That would mean that the acceleration is changing.
Oh, never mind. Displacement.
That's, yeah, I was like, I think that you're actually over here. There's going to be some curviness happening over here, right? So I'm going to work backwards just real quick because we're going to get there. Is that okay? So there's going to be curviness here, which means that there's a non-constant value here. What's the acceleration one going to look like? Constant. Constant at what value? Negative 9.8, right? Something like this. Boom. If the acceleration graph is constant and negative, what does that mean about the slope for the velocity? Constant negative slope. Constant negative slope. What did it start out? What was the velocity that started out as? 0? And then it got more and more and more negative. So really that graph is going to look like, this is good stuff, you guys. This is like thinking stuff. Constant negative slope. It started out at 0 and then it's going to go down, down, down like this, right? Okay. Constant negative slope. Constant negative values for acceleration. Is that all right? All right. This is the tough one. Tell me about the values for V. What are the values doing? They're getting more and more negative, right? More and more negative. So what does that mean about the slopes for the displacement? The values for velocity are getting more and more negative. So that means that the slopes for the displacement need to be getting more and more negative. Where does the frog start out at in this picture? 1.6 meters above the 0 point, right? So he's going to start off somewhere up here. And then time's going to go on. And as time goes on, the slope starts off at 0, and it's going to get more and more and more and more negative. How'd we do? Are we okay? It's curvy graph? Curvy graph. More and more and more negative. So it was at 0, and then it becomes negative, and it becomes, whoa, that's an icky line. Yikes. More negative, and it becomes more negative. It's true. It's true. Okay, we got one more thing to do. Let's do it down here. For the ball, we drew a picture. We drew a picture with lines. The blue lines represented the what? The velocity. Here's my frog. I'll draw him in green. Here's my frog. I'm just going to draw him kind of spaced out on his way to the floor. Not spaced out like he's not paying attention, but spaced out like time between him. Tell me about the speed as he moves down. What are those little arrows going to do? Get bigger as it goes down, right? He's going to get faster and faster. So there's no arrow on that first one, and a little arrow on the second one, and a bigger arrow on the third one, and a super big arrow on the fourth one, right? Here the arrows get bigger or longer because the frog or the ball or the whatever speeds up in the negative direction. Okay. How are we doing? So far, so good? Everything we've done so far was from Unit 1. There you go. Nice review. You're welcome. You got that. All right. Now we're going to go to Unit 2. Welcome to Unit 2. Here it comes. Here's my question. This is question number 3. How long will it take for the frog to hit the ground when I do this? I'm just going to watch now. I'm holding him 1.6 meters above the ground. I'm going to give him a push in the horizontal direction, like that. Okay? So you don't have to do the calculations because you don't know how yet. The question that I'm asking you right now, will it be greater than, less than, or equal to 0.57 seconds? So I'm holding him up 1.6 meters above the ground. I'm going to give him a push like this. Is it going to take more than 0.57 seconds? Less than 0.57 seconds or equal to 0.57 seconds? I want you to make an educated guess, and then I want you to talk to your table mates. Do it right now. Have a conversation. All right. I'm going to take a poll, not because I am going to hold you to this, because that's not what I do, but I'm just kind of finding out where we're at. So raise your hand, ladies and gentlemen, if you feel like it is going to take more than 0.57 seconds for that frog to hit the ground. Raise your hand if you think it's going to be less time. That's never a popular choice. So you got to, cover all your bases. What's the other choice? The same. Who thinks it's going to be the same? Zach is my lone vote that way. All right, Cara, you're coming up here. You can help me out. You look like you need to, move around a little bit. I have this little device here. Need to wear some safety goggles. We just got an email about lab safety yesterday. I want to be a good kid. Don't want anybody to go tell Mrs. Hughes that I'm doing things I'm not supposed to do. Don't want to get in trouble. All right, you ready? You psyched up? You're going to be my human ring stands. Okay. You remember ring stands from chemistry? Yeah, like they hold stuff, so you're going to hold stuff for me. Okay. You're human, you're going to hold stuff. Before you actually take a hold of stuff, I want you to take a look at these 2 ball bearings. You can hold them. Tell me about the mass of them. They're heavy. Yeah. How do they compare with each other?
Actually, one. No.
They feel about the same?
Yeah.
Okay.
Maybe, yeah.
Are they exactly the same?
No.
What's different between them?
These have 2 holes.
Okay. And does that one have holes?
Nope.
Okay. So you're all living vicariously through Cara because she has just observed that there's a hole through this one. There's a hole in this wall, and there's no hole in this one. Okay. But it's interesting. All right. So now I got all this funny little device that somebody in the last period was like, it's kind of like a, what do you call it? Pinball machine. It's kind of like a pinball machine. So it's got a rod here, and then it's got this spring inside, and I can pull this back to like that. And when I pull that back, then you see what happens to the rod. It moves up. Okay. And then when I flip this, then it goes back down. Nothing magical. I just want to make that really clear. Nothing magical here. You can pull it back to like the next one up, and then it goes like that. So you can kind of do lots of different versions. Okay. So you're going to hold this. We're going to make some observations. We're not going to do it from 1.6 meters because it doesn't really matter as long as they're the same height. So you're going to hold it. You want to hold it like right here. That's kind of where you're going to hold it. Okay. So then what we're going to do is I'm going to move this over. We'll move it just to that one for now. And then I'm going to take my ball bearings. I'm going to take the one that's just the one with the hole in it first. I'm going to put it right here. You might want to, I'm going to have you turn like that. Perfect. All right. So everybody see that one that's right there? The ball bearing that's right there. So I'm going to flip this. Not a surprise, perhaps, right? So the rod was going through it. It pulls the other way, and this thing falls straight down. So that's just like the frog that fell straight down. Okay. The nice thing about this, because if I tried to do the frog going this way and the frog going this way, you'd be like, they don't go at the same time, right? You don't trust me a whole lot. But this little device is pretty fancy because the nice thing is that when I move this over, I can put the one ball bearing up here, and then this is the part we have to really focus.
Okay.
But I believe in you. Deal? Mm-hmm. Okay. Then I'm going to put this other one right here, and I'm going to balance it right there. So the nice thing is, right, when I flip this, the rod is going to go this way. So this one is going to fall straight down like the frog that was falling down. This one is going to get a kick in this direction. Are you with me there? Yeah? Okay, so it's going to go this way. So now we've got the two that are going to be released at exactly the same time. The other nice thing about this, I'm going to do it one more time just with the one here, is that if you listen, you can hear when it hits, right? So not only can you look at it, which is nice, but you can also listen for it and see when it hits. Now here's the deal, my dear, is that you have to make sure you're holding it exactly flat.
Okay.
Because if you're not, then the data collection will not work.
Okay.
Okay? So no pressure. I believe in you. So if you guys are way over there, you might want to stand up so you can see a little bit better because it's kind of exciting. I don't know, we're going to find out. So, you ready?
Mm-hmm.
All right, here we go. Oops, you got to move that finger. That was not yours. There you go. 3, 2, 1, go. What did you hear? Or I mean, it doesn't matter where they go.
That one.
Oh, there it is. Thanks, friend.
It's
One more time. Should we do it one more time? What was the observation that you heard that first time? Same time. We'll push it back to the, next one over. Muscles. You're doing a great job. I'm proud of you. I'm excited about this. All right, this one's going to go further. Okay, don't stay right there because I put goggles on. Move this way first. You can go retrieve it after. There you go. All right, here we go.
I get it back.
I don't think it's going to get, that would be quite a trajectory. I don't think that's, I mean, no, I don't know. It's not going to happen. All right, here we go. 3, 2, 1, go. What'd you learn? Same? It's weird, right? Because if you think about the displacement for this, that one went all the way over there. This one kind of rolled after it hit. I don't know where it went. Did you guys find it? Oh, there it is. It's over here. I see that one. So, one. Thank you so much, Cara.
It's okay.
Cara. Let's clap her. Yay, she was the best one. It was lovely. All right. So, I can't put these on either. That's nice. Woo! I like bringing those. Even though the ball that was on this side went really, really far, like its displacement was a lot farther than the one that fell, right? Even though it went this way, the time was the same. That's weird. So the ball that fell went straight down and it sped up, boom, 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 just like this one did, right? It went down, 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 boom. But that one, the other one, the one that went this way, went out and down. Same time, even though it went further. That's kind of interesting, like free stuff. Let's write this down. This is interesting. We're going to call this, here it comes, two-dimensional motion. What? Two-dimensional. All the problems that you've done up till now have been one-dimensional. They've been either going in the x direction, right? The buggy lab, the ball in the hallway, all that stuff was just one-dimensional, horizontal. We've also dropped stuff. We dropped rulers, we dropped balls, we dropped all kinds of stuff. That was all in the vertical direction. 2 dimensions just means we're putting them together. Two-dimensional motion, also known as projectile motion. A projectile is just something that is launched. That's it. It's nothing more fancy than that, okay? Projectile motion or two-dimensional motion. So let's draw what we just saw. So you've got it in your head and you understand kind of what's happening here. So here's the little device. If you want to draw Cara behind it, you're welcome to. She's got the blue shirt on and the cute little pigtail things. So if you want to draw that, you're welcome to. You do not have to. I want to draw, though, I'm going to call this one ball A. That's the one that fell straight down. Okay? And then I'm going to draw ball B. That's the one that went out and down. And just really quickly, before we move on any further, would you draw the trajectory? Do you know what the word trajectory means? No? Anybody know? The trajectory is essentially where it goes. Yeah. So draw kind of where each one of them goes. So A, again, is the one that's going to go straight down. So you can draw that trajectory straight down. So it's just kind of like the map of where it goes. And then ball B kind of went out and down, didn't it? It went something like this. It followed have we said the P word yet? What is that shape? Anybody know? Parabola. Yeah, my math friends are like, I love parabolas. They're so much fun. I'm saying, I know. I totally know. It's super good, right? They are awesome. And there's my floor. So now I want to make sure that I understand what is going on here. And actually, you know what I'm going to do? I'm going to draw one more ball down here. I'm going to call this one C. This is like the ball that we did at the very beginning. That's just going to go doop, 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 in that direction, just so we can kind of keep it all in our heads. Doop, 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 doop. There we go. All right. We're going to put together everything we did at the beginning. We're going to smash it together. We did ball C, and then we did ball A, and now we're going to do ball B, right? So we're going to do C first. We're going to put it all together. Here we go. So ball C, as it's moving, it went here at some point, and it went here at some point, and it went here at some point. And tell me about the velocity as it rolled. What is it, Grace? It's the same. So the little arrows are all going to be the same, right? There's one that goes like this, and the next one's going to be the same length because there's no change in velocity. They just keep on trucking. Again, we're assuming no friction. We're assuming no air resistance because we like to work in a vacuum. Okay? It's not a good literal plan, but it is a nice physics plan. Okay? Let's talk about ball A. That's like the frog that was falling. So here it is at some point. Here it is at some point. Here it is at some point. Draw those arrows. Tell me about the speed of ball A in each of these cases. Okay? What's going to happen to ball A's speed? That's not a happy noise. Oh, okay. Is this a practice or is it?
Yeah, it's, I don't know.
Something. Okay, that's cool.
It's going
Yay.
to increase.
Good times. All right. Tell me about the speed on ball A. What were you gonna say?
It's going to increase.
It gets bigger and bigger and bigger, right? So here we go. It's going to be 0 at A. It's a little bit at B or down there. Boop, boop, boop. It gets bigger and bigger and bigger. How are we doing? So far, so good? Okay. And now we're going to draw ball B, the one that we were paying attention to. I'm going to just make some convenient lines here, just so that I can kind of do my heights. Just kind of lining it up there. So I've got the ball there, and I've got it there, and I've got it there. Now here's the fun part, friends, is that ball B is a combination of the story of C and the story of A. So at the very moment after I flip that little switch, does ball B have any velocity? After I flip the switch, it gets a kick. Does it? What direction is its velocity in? Which way did it get the kick? This way? Does that make sense? Okay. The reason, let's go back to ball C for just a second, because I think we said this, but I want to make sure it's really clear. All of these arrows on ball C have the same length because the speed is constant. Saying that the speed is constant means that there is no acceleration in the x direction. In order for there to be acceleration, there has to be something pulling or pushing on it. There's nothing pulling or pushing on the ball in C. In the x direction, is there anything pulling or pushing on ball B after the kick happens? After the kick happens, Megan's like, not so much, right? The kick pushes on it, right? That's what we're going to do in Unit 3. Just wait for it. We'll get there. I promise it'll be great. But until that moment, let's just talk about after the kick happened. It's got velocity here. Tell me about the velocity here. Is it the same? In the x direction? In the x direction? Does it have anything speeding it up or slowing it down in the x direction? Anything pulling or pushing on it in the x direction? No. It would mean that it has like a little parachute or it has a little jetpack. And Kara looked at these spheres, and did you see any parachutes or jetpacks? No. She's like, are you talking about? No.
First I was like questioning myself, like, wait a minute.
Did I miss something? No, there isn't. There aren't any parachutes. There aren't any jetpacks. It's all good. There is nothing speeding up or slowing down this sphere in the X direction. It's going to be constant. Constant. Same speed in the X direction the entire story. Bless you. What about the Y direction, though? The ball that went like this, when I let it go, does it have any velocity in the downward direction when I let it go? That's a weird question, guys. Watch. I want you to watch the frog. Let's see if I can launch in here. I don't know if I'm this good. I've never tried. It's never been tried before. First time for everything. I don't think it's gonna work. Twitching like that. This is kind of weird. I don't know. So after I let him go, I'm gonna hit him straight horizontally. Tell me if right here as he's leaving, does he have any velocity in the down or up direction? That didn't work very well. What's it supposed to be? He does not. Except for the spinning. That's like unit 7. We're not there yet. We'll get there, but not yet. What's that? I mean, it's a while from now. It's not today. Rotational motion? Whee! Not today. No velocity in the Y direction. As it falls, though, what happens to its velocity in the Y direction? What happens to its velocity in the Y direction? It gets bigger and bigger and bigger. Let's write it down. It gets bigger and bigger and bigger. Make sure you got that picture drawn. Ladies and gentlemen, are you going to come to this room tomorrow for class? No. Where are you going to meet me? At the stadium. I'll see you there tomorrow. Have a great day.